So, ionic compounds. Whoop, whoop. Properties and the ionic bonding model. And we're going to use the bonding model to explain the different properties of the ionic bonding model, similar to what we did with metals. So it's hardness, high melting point, difference in electrical conductivity dependent on states, right? Reference to formation, nature of ionic bonding, crystal structure, limitations of representations, and uses. To describe the model, explain how ions are produced, chemical formulas, and describing the uses. So lots of this you've already done. It was in your transition pack, so hopefully, particularly formulas of ionic compounds. Yeah, lots of that was in your transition pack, so we can move through this relatively quickly. Ion simply means a charged particle, coined by Michael Faraday. That's not important, it's just interest. Common ionic compounds. Rocks, minerals, gemstones, and all of our different common salts. Sodium chloride, known as table salt. Potassium chloride, often called rock salt or low sodium salt. So when you see low sodium salt, it's probably going to be a mixture of sodium and potassium chloride. Gemstones, rocks, minerals, things like tiling, so ceramics are typically ionic as well. Characteristics of a salt. So we refer to a salt as being typically a metal and non-metal in nature. Sodium bromide, calcium chloride, potassium oxide are all salts or ionic compounds. In reality, go back. We can have other salts that are not simply metal and non-metal, right? So an ionic bond or an ionic compound is not metal and non-metal. It's cation and anion, yeah, to be more particular. Because there's not a single metal in this compound, ammonium chloride. So ammonium is a polyatomic ion. If we break down that word, atomic means atom, cation, positively charged, poly means many. It's an ion made up of many atoms. Yeah, make sense? Properties, high melting and boiling point. What does that tell us about a substance? The bonds between the particles are very strong. Hardness means we can scratch something which is softer. Brittle means what? Right. Brittle means it's organized. Oh, sorry, hardness is what I asked. Yeah, so we've got this regular, really strong bonding between particles, so it's got huge amounts of compressive strength. Brittleness means it breaks apart very easily when hit with a sharp force. So, I'm trying to think if there's any ionic compounds in the room. There isn't. It's all polymers. So let's say this was stone. It's not. It's a laminate. But let's say it was stone. Stone is a type of ionic compound. It can hold a lot of weight, but if I put a sharp force to it, it will break. Yeah. Glass is not. Glass is covalent. So glass is actually covalent. It's a mega molecule made up of silicon dioxide. So we'll talk about that later. So they do not conduct electricity in the solid state. What does that tell us? Not about electrons. No free moving charged particles. So it's not always about electrons moving. A charged particle can conduct an electrical charge. So they will conduct electricity if they are molten or aqueous, so if they're dissolved in water or if they are in their liquid ionic form. Structure, we call it crystal or a crystal lattice structure. Lattice means a regular arrangement.
Is it the salt in the ocean that conducts electricity?
Yeah. Yeah, so all the different ions, not limited to sodium chloride, but nitrates and sodium ions and potassium ions and calcium ions and all the different ions have the ability to move charge, or it's for negative charge in particular. So sodium chloride on and that atomic scale is actually cubic. So if we zoom right in, we can see that salt naturally forms cubic structures. That's what it looks like, yeah. Naturally cubic structures.
That's not going to really.
Yeah, and we've got, if we were to zoom in further, so this is 6 micrometers, so 6 millionths of a meter. And we think about an atomic size is in the nanometer scale, right? So say 10 nanometers across. So we've got to think that one of those small cubes might be 1,000 atoms in length. The ionic bonding model, crystal lattice structure, regular arrangement. It's this regular arrangement of alternating ions according to its ratio. Right? What I mean by that is in the example of sodium chloride, there's 1 sodium ion to every 1 chloride ion. So it's a 1-to-1 ratio. In, say, lithium oxide, you would have 2 lithiums to every oxide ion. Does that make sense? Yeah? In, say, aluminium sulfate, you would have 2 aluminium ions to every 3 sulfate ions. Yeah? As per your ionic formula is how the structure would be made up. So we've got slightly different weird and wonderful structures of ionic compounds, the simplest of which is 1-to-1, which would be cubic. Make sense? Yeah? Ish. A ball and stick model helps to represent the bonding between the ions. Then we can look at space filling models to show the relative size of the ions themselves. We can see that chloride is significantly larger than sodium. And it's held together by what? How is the lattice held together? By the bonds. What are the bonds called? Here's a hint. It's the same as metals. Electrostatic forces of attraction. So it's same in that regard to metals. So metals, it's the electrons and the cations. In ionic bonding, it's the force of attraction between opposed charges. So opposite charges attract. No, ionic compounds don't form discrete molecules. Molecules is a discrete unit. So there's no particular N. It's not simply 1 sodium atom and 1 chlorine atom together, but it's many. But we represent it in its what's called empirical formula that we'll get to in our next topic. So it's our smallest ratio of particles that we represent our formula to. Ion formation. Hopefully this makes sense. Sodium atoms want to lose their outer shell electrons. Chlorine, group 17, wants to gain one. So we've got this transfer of... Anyone got their charger? All right, thanks. Let's move on. Oops, can't do that. Let's show screen. Positively charged ions, non-metal atoms become negatively or anions. So cation, cats are positive. Positive. Yeah? No? Really lost on you. Cats have pores. Cations are positive. Yeah. Charge of the ions referred to as its electrovalency. You don't get an electrovalency table in year 11.
What is an you just have to read the
You do not get the table. You do not get the ion table in year 11. Do not. You remember the common ions. Standard notation is you list the cation first in the formula. So iron 3 oxide would be Fe2O3 as our example. This is not on the test next week. Test is chapters 1, 2, density, sig figs. So the first week where we did all those little skills and had the little pracs and stuff like that, that will be on the test. So sig fix and density, and then chapters 1 and 2.
Do you need to know like the results from the graph?
No, you don't need to know the pracs, it's the skills from the pracs. So safety errors. Emission spectra will be on the test.
That was the only part I
Okay. As I said, we'll have a revision session. Sodium metal reacts with chlorine gas, the ionic compound, sodium chloride. Sodium, highly reactive. Chlorine, reasonably reactive. Sodium chloride, stable, unreactive. Really high melting boiling points. Sodium, melting point, about 80 degrees. Chlorine, melting point, negative something, right? Melting point of sodium chloride, 800 degrees. So we can see that the properties of the compound is not the same as the constituents that make it up. This should look fairly familiar from last year, those who did chem. Sodium donates 1 to chlorine, goes to our ions. The electron configuration is the same as the nearest noble gas. Magnesium, similar. Donates 2 to oxygen to form magnesium oxide. If we have magnesium chloride, it's MgCl2. It's going to donate 1 electron to each given chlorine atom and that force of attraction between the ions. Some common ions. Note that the number is listed first, so standard notation. If it's a +2 charge, it's element 2 plus in superscript. Notice with our transition metals, we need to indicate what the charge is. Group 1, Group 2, Group 13 will be a 1, a 2 plus, or a 3 plus charge. Our transition metals, we specify copper 1 using Roman numerals, or copper 2, iron 2 or iron 3, nickel 2 or nickel 1, nickel 3, tin 2, tin 4, and so on. Lead 2, lead 4, whatever it might be. Okay, chromium 2 or chromium 3, chromium 4, chromium 7, right? So the number will indicate the charge on the ion. Formatting is really important in chemistry, right? Subscript tells us how many atoms. Superscript tells us the charge. If we go superscript on the left-hand side, it tells us the mass number. Subscript on the left-hand side tells us the atomic number. Common ions, ones I would expect you to know. Hydroxide, sulfate, carbonate, nitrate. Halogens, that you can determine that from the periodic table. All of the ides you can determine from the periodic table. And here's a hint. If you know what sulfate is, then sulfite is 1 less oxygen and the same charge. So sulfite is SO3, same charge as sulfate, 2 minus. If we look at same thing with nitrate. Nitrate, NO3 minus. Nitrite, NO2 minus. Some slightly less common ones that I would expect you to know: permanganate, MnO4 minus, and dichromate, Cr2O7, 2 minus. Polyatomic ions, we said that, made up of more than one atom. Balancing, right? It's all about balancing the charge. Balancing polyatomic ions. Group the polyatomic ion in brackets if you are going to have more than one. Common mistake was, particularly with hydroxide, was going OH and then putting the 3, which would imply 3 hydrogens, 1 oxygen, not 3 hydroxide ions. Okay. I'll pause that.